You know, a dyno is nothing more than a gauge or a meter. It measures engine horsepower and torque, but it can also hold a steady load, so you can micro-tune individual cells in your fuel and spark XY tables, and a whole lot more. But a dyno, in and of itself, does not make any more horsepower or torque. A flow bench will measure the amount of air a port can flow. It can do it at different depressions, different valve lifts. It can help isolate lazy dead zones, hypersonic choke points. But in and of itself, it doesn't help anything flow any better. A scan tool is nothing more than a gauge or a meter. It can read diagnostic codes. It can clear them. It can read pending codes, ScanTool data, and a whole lot more. But in and of itself, it doesn't fix anything. It's just a tool. Since this section's on scan tools, that's where we're going to focus. Now, the scan tool that we all know is assigned to OBD II, Onboard Diagnostics Generation 2. And it makes sense if there's an OBD II, there at one point in time had to be an OBD I, right? Okay. OBD I would be 1995 model year vehicles and older. It also includes heavy-duty trucks, 96 and up to some point. Prior to OBD II, any diagnostics that you would find in a vehicle were specified by the manufacturer. Early fuel injection systems didn't even have diagnostics. If there was a problem, the technician had to poke and prod around with meters, oscilloscope, and pretty much figure it out on his own. Some of the car companies started going with trouble codes. So at least you got like a code 13 coolant temp circuit or something that pointed the technician in the right direction. And then we got data stream information where if it had a coolant temp sensor code, the technician could look and see what does the computer see for engine coolant temperature. General Motors was the most progressive. They had a connector, ALDL they called it, Assembly Line Diagnostic Link. And they had a special tool that the dealers would get so that they could plug into that and get codes and get data. Ford had their version. The GM tool didn't work on the Ford vehicles, and the Ford tool didn't work on GM or Chrysler. And so that was kind of a hodgepodge. A good mechanic had to have everybody's tools, and they had to remember all the codes. And so somewhere in the 1980s, the Society of Automotive Engineers started looking at this. They kind of weighed out the vehicles that seemed to be easiest to fix in the shops. And they found GM just made it so easy between the trouble codes and the data stream information. So they got together and they decided they're going to standardize this whole diagnostic thing. And for the 1996 model year, we get OBD II. OBD II standardized the connector. It's the J1962 connector, and usually it's found underneath the dash. That was even something in OBD I. Sometimes it was under the dash, sometimes it was under the hood, sometimes you had to lift the carpet to get to it. But the connector goes under the dash. It's the same connector for every vehicle. Ford, GM, Chrysler, Toyota, Honda, Jaguar, BMW, doesn't matter. The actual communications protocol has also been standardized. It's the J1699. You have standardized codes. So P, what is it, 0131 or something like that. Oxygen sensor lean. That's the same code on a Ford, Honda, Toyota, Chrysler, doesn't matter. If the scan tool wants to ask the computer for a mass airflow sensor value, it's hexadecimal 000F on everything. So the PIDs are all the same. This made it a lot simpler for the technicians because they only had to learn one process, and it was the same for every vehicle. But again, we're not going to actually fix anything with the scan tool, but this segment is to try to help you to figure out how to use it to your benefit so that you do get the fuel economy gains. Now, the scan tool is going to give you diagnostic trouble codes, be able to clear them. Pending codes, be able to check the readiness monitors, data stream information, vehicle information, like the VIN, the odometer reading, calibration data, all kinds of stuff like that. Plus, it's able to tie into not just the engine controller, but transmission controller, airbag module, anti-lock braking module, body control module, and a whole lot more. You can roll the windows up and down with a good scan tool. So what we're going to focus on is how to use the scan tool while improving a vehicle's combustion efficiency, where the scan tool helps us to figure out if we did it right, did it wrong, if we're on the right track, and so forth. Now, before we modify a vehicle, we definitely want to ensure that it's in good operating condition. The scan tool can help us see what's going on without tearing into much of anything. So we're going to check for diagnostic trouble codes, pending codes, and readiness monitors before we do much of anything else. And then with the engine kind of cold, we're going to plug in, turn the key on, but not start, just turn the key on. Then we're going to go into the data stream. We're going to look at oxygen sensor values first. If you have a narrowband oxygen sensor, it'll probably say something totally unreasonable like 420 millivolts. Widebands, AFRs may say 0. You want to make sure, because the engine's cold, the oxygen sensors need 660 degrees or so Fahrenheit to work. You want to make sure that you don't have any oddball readings there. Look at your loop status. It should be open loop normal. You have open loop with fault. You have closed loop normal, closed loop with fault. I think there's a total of 7 different possibilities on that. Then look at like barometric pressure. You should have a barometric pressure reading on most vehicles, and you can just check your local weather service to see what the barometric pressure is where you are. It should be pretty close. Then we want to look at temperatures, air intake, coolant. If you have like an HVAC sensor, cat temp, anything that's temperature related, we want to make sure that they're all pretty close to the same. They may be a degree or two off. It actually will increment, and I think 2 degrees Celsius. So, you know, if it's off 2 or 4 degrees, that's no concern. Then we're going to do a throttle sweep. Now we're going to look at our throttle position sensor, TPS. And the older cable actuated throttle vehicles will have one value for that. Throttle position. It could be volts or actual angle, or it could be percent. But you'll have one value. The newer drive-by-wire, you'll have throttle request A, throttle request B, throttle position A, throttle position B. So what we want to do is we want to just slowly step down on the throttle the whole way to the floor and watch those numbers. They should just gradually change with your foot. And then back off slowly. Watch for a hiccup, because a hiccup is going to be a bad spot in the resistive wiper. And just basically go down through and look at all of the data. If you have a map sensor, it should be reading barometric pressure, usually in kilopascals. Ambient sea level is like 101 kilopascals. So you're probably going to be in the high 90s for most of like North America. In the mountains, it'll be less. Again, weather service will tell you where you should be. If you have a mass airflow sensor, it should be reading 0 grams per second because the engine's not running. So you just kind of go down through and look at all the values before you start it.